On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System detected an object moving through our solar system with a hyperbolic trajectory, eccentricity of approximately 1.000016. This marks the third confirmed interstellar object observed passing through our solar system, designated C/2025N1, or more commonly, 3I Atlas. As of October 24th, 2025, this object is undergoing solar conjunction, positioned on the opposite side of the Sun relative to Earth. On October 29th, it will reach perihelion at 1.36 astronomical units, approximately 203 million kilometers from the Sun. This video presents a comprehensive scientific analysis of 3I Atlas based on published observations from multiple space agencies, peer-reviewed research, and data from ground-based and space-based telescopes. We'll examine its physical properties, chemical composition, orbital mechanics, and the ongoing scientific debate about its formation and behavior. 3I Atlas was first detected on July 1st, 2025 by the Atlas Survey, a NASA-funded network consisting of 4 robotic telescopes, 2 in Hawaii, 1 in Chile, and 1 in South Africa. Initial photometric measurements indicated an object moving at 44 kilometers per second relative to the solar system's barycenter, with a trajectory inconsistent with solar gravitational binding. Follow-up observations by multiple observatories confirmed its interstellar origin within 48 hours of discovery. Orbital characteristics. Current orbital elements as of Julian date 2,460,875.5. July 18th, 2025. Eccentricity 1.000016 plus or minus 0.000003. Hyperbolic. Semi-major axis, negative 630 AU, negative indicates unbound orbit. Perihelion distance, 1.359 AU, 203.4 million kilometers. Perihelion date, October 29th, 2025, plus or minus 0.2 days. Inclination, 4.82 degrees relative to ecliptic. Incoming velocity at infinity, 44.1 plus or minus 0.3 kilometers per second. This hyperbolic trajectory confirms the object is not gravitationally bound to the Sun and will exit the solar system following perihelion passage. Comparative analysis with previous interstellar objects. 3 interstellar objects have now been confirmed. Oumuamua, 2017. Velocity, 26.3 kilometers per second. Perihelion, 0.255 astronomical units. Estimated mass, approximately 10 to the power of 9 kilograms, showed non-gravitational acceleration without visible outgassing. Axial ratio, 6 to 10, elongated Borisov, 2019. Velocity, 32.2 kilometers per second. Perihelion, 2.006 astronomical units. Estimated mass, approximately 10 to the 12th kilograms, displayed typical cometary features with bright coma and tail. Composition similar to solar system comets 3I Atlas, 2025. Velocity, 44.1 kilometers per second. Perihelion, 1.359 astronomical units. Estimated mass, greater than 3.3 times 10 to the 13th kilograms, based on minimum 5-kilometer diameter. Active coma observed from 6.4 astronomical units. Unusual anti-sunward jet, documented July-August 2025. Statistical significance. 3. I-Atlas moves 40% faster than Oumuamua and carries approximately 33,000 times more mass while displaying intermediate perihelion distance between the 2 previous objects. Trajectory. Origin. Dynamical backtracking conducted by Perez-Couto et al. 2025 traced 3I Atlas's path 10 million years into the past. The object's incoming vector originates from the Sagittarius constellation, the direction of the galactic center. However, due to the significant time span and gravitational perturbations from nearby stars, identifying a specific stellar origin remains computationally infeasible with current astrometric precision. Photometric observations. Initial brightness measurements in July 2025 showed 3I Atlas at apparent magnitude 17.5, brightening to magnitude 12 to 13 by October as it approached perihelion. Size estimation based on absolute magnitude and assumed albedo. Minimum nuclear diameter, 5.0 plus or minus 0.8 kilometers, assuming albedo of 0.04, typical for cometary nuclei. Surface area, approximately 78.5 square kilometers. This makes 3I Atlas significantly larger than Oumuamua, estimated 230 meters, maximum dimension, and comparable to Borisov, estimated 1.4 kilometers diameter. Spectroscopic analysis. James Webb Space Telescope NIR-SPEC observations conducted on August 6, 2025, at heliocentric distance 3.32 astronomical units provided definitive compositional data. Gas composition by mass fraction. CO2, carbon dioxide, 87.2% plus or minus 2.1%. CO, carbon monoxide, 9.1% plus or minus 1.3%. H2O, water, 4.3% plus or minus 0.8%. Trace species, HCN, CH3OH detected at less than 0.4%. This composition is carbon-rich compared to typical solar system comets, which generally show H2O dominance. However, it falls within known ranges for long-period comets formed in outer planetary regions. Mass loss rate, 150 plus or minus 25 kilograms per second at 3.32 astronomical units, measured via spectral line intensities. The James Clerk Maxwell telescope detected hydrogen cyanide, HCN, production. September 7, 2025, 2.33 astronomical units, 1.5 plus or minus 0.5 times 10 to the 25th molecules per second. September 14, 2025, 4.5 plus or minus 1.9 times 10 to the 25th power molecules per second. Rate increase consistent with R to the negative second solar heating model. Coma dynamics. Hubble Space Telescope high-resolution imaging from July 21, 2025 resolved the inner coma structure. Coma diameter, approximately 12,000 kilometers at nuclear region. Dust production rate, 10 to 50 kilograms per second based on scattered light models. Color, slightly reddish, JWST 0.68 plus or minus 0.12 magnitude, typical for cometary dust. Gemini South observations from August 2025 measured an anti-solar tail extending 56,000 kilometers with angular length of 30 arcseconds. Thermal analysis. At perihelion, 1.36 astronomical units, solar flux received by 3I Atlas. Incident power, 33.7 gigawatts, assuming 5-kilometer diameter, 0.04 albedo. Peak surface temperature, approximately 230 to 280 Kelvin, sufficient for CO2 sublimation. Frost point, 194.65 Kelvin at 5.18 bar. This thermal input drives the observed outgassing, with sublimation rate exponentially dependent on surface temperature following the Clausius-Clapeyron equation. Observational evidence. Between July and August 2025, Hubble Space Telescope imaging revealed a morphological feature unprecedented in cometary observations, a jet structure oriented toward the Sun rather than away from it. Hubble July 21, 2025 observations, projected elongation, 2:1 in plane of sky, viewing angle, corrected 3D elongation, approximately 10:1, linear extent, 10,000 kilometers from nuclear photocenter, position angle, within 15 degrees of sun direction. This anti-tail persisted through August 2025, before transitioning to a conventional anti-sunward tail configuration by September 2025. Theoretical framework. Loeb-Keto model. Astrophysicists Avi Loeb and Keto, Harvard-Smithsonian Center for Astrophysics, published a theoretical model in October 2025, explaining this phenomenon through sublimation physics. Model parameters. Primary volatile, C, O2 ice with sublimation temperature approximately 195 Kelvin. Secondary component, H2O ice grains entrained in CO2 gas flow. Grain sizes 10 to 100 micrometers, optimal for scattering solar radiation. Physical mechanism. 1. Solar heating causes rapid CO2 sublimation on sunward hemisphere. 2. High-pressure gas flow ejects H2O ice fragments at velocities 10 to 100 meters per second. 3. Ice fragments remain solid in sunward direction due to short residence time in flow, less than 10 to the power of 3 seconds. Radiative cooling insufficient for complete sublimation. 4. Fragments strongly scatter sunlight, creating visible anti-tail transition to normal tail. September 2025. As heliocentric distance decreased below 2.5 astronomical units, exponentially increasing sublimation rate, decreased ice grain lifetime, sublimation becomes dominant. Refractory dust particles, longer lived, form conventional tail. Solar radiation pressure pushes dust anti-sunward. Quantitative validation model predictions matched observational data. Peak scattering cross-section at 3 to 4 astronomical units. Confirmed. Transition timing to anti-sunward tail. Confirmed. September 2025. Spectroscopic CO2/H2O ratio. Confirmed. 87 to 4 by mass. Alternative explanations considered and rejected. Optical illusion from viewing geometry. No. Jet orientation tracked across multiple viewing angles. Electric field effects. No. Insufficient ionization at greater than 3 AU. Radiation pressure on large grains. No. Requires grain sizes greater than 1 millimeter, inconsistent with scattering efficiency. The Loeb-Keto model represents the current scientific consensus explanation, published in peer-reviewed astrophysical literature and consistent with known comet physics. Interstellar object population. Statistics. With 3 confirmed detections in 8 years, we can estimate the flux of interstellar objects through the inner solar system. Detection rate, 0.375 objects per year, 3 in 8 years. Estimated population, 10 to the power of 4 to 10 to the 6th objects greater than 100 meters diameter per cubic parsec. This suggests hundreds to thousands of interstellar objects pass within Jupiter's orbit annually, with most remaining undetected due to small size below detection thresholds, low albedo, dark surfaces, high velocities, limited observation, windows, faintness at large heliocentric distances. The Vera C. Rubin Observatory, beginning operations in 2025 to 2026, will increase detection rates by factor of 10 to 100, potentially identifying dozens of interstellar objects per year. Formation. Scenarios for interstellar comets. 3-Odir Atlas likely formed in the outer regions of another stellar system and was dynamically ejected through 1. Planetary scattering. Giant planets gravitationally eject planetesimals during system formation. Efficiency, 10 to 50% of initial mass. 2. Stellar encounters. Close passages with neighboring stars perturb Oort cloud analogs. Frequency, once per 10 to the 6th years for sun-like stars. 3. Galactic tidal forces. Differential gravitational potential across extended comet clouds, effective beyond approximately 50,000. AU. The CO2-rich composition suggests formation at temperatures 20 to 40 kilometers, consistent with outer planetary regions, beyond 20 to 30 astronomical units from sun-like stars. Scientific consensus. On 3-O's Atlas Nature. Survey of published literature and conference presentations indicates approximately 95% of planetary scientists classify 3I Atlas as natural comet. Approximately 4% consider data insufficient for definitive classification. Approximately 1% explicitly propose non-natural origin hypotheses. This distribution reflects standard scientific conservatism. Extraordinary claims require extraordinary evidence. Current observations are consistent with known cometary physics, though some features, large mass, ecliptic alignment, anti-tail, are statistically unusual but not impossible. Conclusion. 3. Atlas represents a scientifically valuable laboratory for studying extrasolar planetary system formation and evolution. Its chemical composition, physical properties, and dynamic behavior provide direct sampling of material formed around another star billions of years ago. Post-perihelion observations over the next 4 months will either A. Confirm conventional cometary behavior, adding to our understanding of interstellar comet population. B. Reveal genuinely anomalous characteristics requiring new physical models. Either outcome advances scientific knowledge and demonstrates the self-correcting nature of evidence-based inquiry. The data will decide.